given two images, how we can estimate the global motion. Okay, so so this motion, when we are going to estimate, we are going to use all the points in the image. Optical flow, we are estimating just looking at one point and small neighborhood around that, and this will be a parametric flow that we'll get equations. As you saw, there were equations. Once we know that, then we can find this motion for any pixel. We can do affine, we can do projective, we can do all other things. So global motion can be removed, as I told you. You can remove camera ego motion, you can do segmentation, find the moving objects, and you can generate mosaics. You can stitch the images together to generate mosaic and lots of things. So suppose here's the example I gave you the first day in the lecture. So there is this UAV video going through, and what we are doing, that we are finding the mosaic incrementally and building this, and this will be a mosaic for all these images in this video. And the way it is that we take the first image and find the transformation between first and second, and let me play this again, and so you will see that this image on the bottom left is the transformed version of the original image there, so that these images are being stacked together, and it is kind of making a mosaic. And that transformation we are going to estimate, and that's a affine transformation between these two images. Okay, so we're going to talk about how to estimate that. And in this case, affine transformation is okay because it's orthographic projection. It's very far from the scene, and we don't have to worry about the depth and so on. Okay, so then we have another example. This is an IR video. So again, as you see, we are incrementally building these depending on the translation, rotation, scaling. So these are modified. These images are modified. There was a lot of, changes there. Yes.
So do you follow actually one car at that point?
No, right now we are just looking at the whole image, and we are just removing the global motion, and then we will, next thing we will do is that. So see, now on the right side, everything's moving, and we got rid of the global motion. Then we can detect the car, only car moving. So that's the idea. And so this is another example. So we have, say, 16 images, and we can stitch them together and make up this mosaic like that. So it's a lot of fun. Huh? It's good? Okay, great. So you have to put up with these equations. Okay, so we are going to talk about, yeah, do you have a question?
I guess all those examples were planar.
Yeah, planar, the orthographic projection. Yeah, so they, they have much more complicated cases where you need, the perspective projection, the homography.
And we won't be doing that?
I mean, I'll tell you how to estimate, and that will be not the exact, some approximation, but they'll be better than affine. So that's actually other half of this. So what we are going to talk about, first method will be Bergan's method, which is using affine transformation. Then we'll talk about Main and Picard method. These are the authors, and that will estimate the projected transformation. Now in that we have approximations. One is pseudo perspective, as we talk about, to one approximation of projective is biquadratic, then the bilinear and pseudo perspective. So that's another one in bilinear and so on. And then we will talk about this notion of image warping, because the whole idea is that you estimate a transformation, then you want to apply the transformation to the image so that you can change it, so that you can stitch these together, a warping. Take one image, apply transformation, you change the image, and that's what, as I show you, the image was looking, like a straight like this and like that, and that's called warping. Okay, so and the applications, mosaics, and so on. So let's get it started. I will do this again next week, but let's get started. So we have two images, image at t minus 1 and image at t. So this image at t and the image at t minus 1. And we have a point xy, and the corresponding point xy is here, which is called x prime y prime. And what we are going to do is this point, we are going to say the motion between these two images is affine. Now here we are modeling the optical flow is the affine, and the optical flow, which is u and v, is affine a1, a2, a1x, a2y, b1, and a3x, a4y, b2. So again, we have 6 parameter, and we are saying the optical flow is affine between these two images. And now we know the optical flow. Essentially, if you know the location in the first image x and second image x prime, optical flow is basically displacement between two. So it's a x minus x prime. So that also can be represented by this: u is equal to x minus x bar, y minus y, v is equal to y minus y bar. So this is affine transformation. Optical flow is affine, and we can represent like this. So what we are going to do is we are taking this affine and we are going to look at like this. We can write down in this matrix form also. So these are the unknowns. We want to estimate using these two images. We want to estimate these 6 unknowns, and we can write down these two equations like this, because if you multiply this with that, you will get that. Multiply this with that, you will get that. So there are 6 unknowns, and we have x, y, and so on. So now, and we can simplify that, say u is equal to big matrix X, and the A is parameter vector, which is 6 unknowns. Again, the same thing. And now we are going to bring in what you learned, optical flow constraint equation. So this is the equation that at each point, the optical flow is defined fxu plus fyv is equal to minus ft. That's what we use for the Lucas-Canade. So we are going to estimate this affine transformation, which is essentially estimate the A, which are the 6 parameters between these two images, by looking at each point, each pixel in the image, so that it satisfies this optical flow constraint equation. fxu plus fyv plus ft should be small. If the motion is correct, then it should be 0. But if it is not exact, then it should be square of that should be small number. It's the same thing we use for the Lucas-Canade. So this is same. Now in this one, what we are going to do, the u we are going to say is affine. We are going to introduce that affine. And so now u will become the x multiplied by a. That's our u. The x matrix and the a is the parameters. Okay? So this is very interesting, because the same thing we learned, we are doing this for all the pixels, but there we were finding uv for every pixel. So we are doing this locally. Now we are going to do for the whole image, and we are going to estimate those A for the whole image, then we can find optical flow for every pixel. That's the beauty of this. Okay? So this is then easy. Say we want to, this is the same thing we can do. Now what we are going to do, instead of just estimating A, which are the parameters of the affine transformation in one shot, we are going to estimate in iterative fashion. We are going to start some initial estimate of this transformation, and we will make some change and look at how good is that change. We keep adding, so that will be better as compared to we just do once. Okay, so this instead of A, we are going to put a delta A. So we are going to estimate delta A, which is a change in 6 motion parameters, and the same equation is shown here. So now we have again a function, and we want to find the unknowns, which are delta A, and we want to minimize the function. Okay? So then, as you know, that whenever we do, then we do what? To minimize the function, you differentiate it with respect to the parameter you want to find, and here that parameter is delta A. So that's what you are going to do. So if you differentiate this with respect to delta A, you are going to get this, and that will be the part of the homework. And it's pretty simple because it's a function. Derivative of any square function is 2, that thing. Then you go inside and differentiate this thing. This is constant, 0. Then you differentiate this one, and you get like that. And then equal to 0, and that becomes your system. And this way, now in this thing, everything is known. Fx, Fy, Ft is known. You can compute from the image. And x is these x coordinates, as you saw there. And this was your x matrix. This is x matrix. These are just x coordinates for each pixel. So therefore, then that's it. You have the finding the A or delta A is just a linear system. A will be a big matrix. Everything is known in terms of Fx, Fy. B is on the right side also. Fx, Ft is known. You can compute. And x is coordinates. That is your first method to find a affine transformation given 2 images. Just compute Fx, Fy, Ft. You're done. And it fits nicely what we have been talking about. Everything you need to do is just compute derivatives. And we are not just saying, well, compute affine, but we have derived it. Say, well, why affine? What does it represent? And under what projection it is valid, and so on. So that is the beauty of science. Okay, so a couple of questions and we end. So equations, you like equations by now, is that right? It's good? Because you just have to start liking the equations. And that's that's a big problem, I think, here, that people are so scared of math, but it's good for you. Yeah, go ahead.
I didn't understand how to get the A from delta A.
Yeah, so we are going to go in detail, how this works, but it's a general. This is valid. This thing is valid, as you know. So we are here up to here. So now we are saying that while we have a affine transformation, for that we can use the optical constant equation. We fill in, and we want to estimate the A. Now, instead of that, we are saying, well, somebody gave us what's A, initial estimate. So we already apply the transformation to this image, and it's already warped. Then we want to find out, is there any residual transformation, which is delta A. So then we'll compute that, and it's the same thing, just a different name, but with a smaller transformation, and we keep doing. Okay, so we started talking about how to estimate the global motion given 2 frames. So we will finish that discussion, and what we were talking about is I don't know what was the problem here. We want to estimate what is called affine transformation. So we are assuming the optical flow is given by affine. Yeah. So the affine transformation, the optical flow is given by these two equations. So the form of affine is that you have 2 by 2 matrix, and then you have this vector, and this is normally is translation, and this captures the rotation and other things. So we are saying U is given by this and V is given by this, and we can write down this kind of equation as you saw. So one thing you have to realize that this is the optical flow is affine. Previously we discussed displacement model where the x, y given, we can find the x prime, y prime was affine transformation of x, y. And we will maybe talk a little bit later about that, but make sure that you understand that U is equal to this, V is equal to that. Previously we have x bar is equal to this, y bar is equal to that. So this one is the displacement, new location, and other is the actual velocity, the velocity in x direction, velocity in y direction, even though they are related. Okay, so we will discuss this particular method from Bergan and others, and that method will use this representation that we can take these two equations and write down like this. So we have a vector on the left, which is a 2 by 1 vector, and then we have matrix which we'll call X. It's a 2 by 6 matrix, and then we have vector 6 by 1. So the vector is the unknown parameters which we want to estimate from the given two images, and these are the A1, A2, A3, A4, and B1, B2. So as you see, if I take this vector, multiply with first row, I'll get first equation, multiply with second row, I'll get second equation. So there's another form of writing these two equations, which is simple. So we'll call the matrix X a vector A, and that U and V will call U. These are the vectors, and X is a matrix. So the question is that, how do we estimate that motion? So we know that we have discussed at length the optical flow constraint equation. Given two images, we can compute spatial temporal derivatives, fx, fy, ft. Then this is true for every pixel, and we are going to use that. So what we are going to do, that we will use all the pixels in the image. This is a global motion, and that U right now is not just one vector, but it's a parametric motion model which is given by this. We want to estimate the unknown parameters in this such that this satisfies this equation at every pixel. So if that estimate U x of x and a is correct, then every pixel should satisfy that and should be 0, and we sum up all that, square of that will be 0. Yes?
What is the input into U? Is that a vector of?
Input, U is just, we define that U is given, we want to estimate A. Once we know A, then we can find out the affine transformation, because A are the parameters. So input is two images. We're given two images, we compute fx, fy, ft. Yes? From there we want to come up with A, which is 6 parameters. Once we know A, then we know the U, the uppercase U, which is at every pixel we can find what is the motion by putting in the value of particular pixel location xy. So xy is location of pixel. If you know the location, if you know the 6 parameters, we can find optical flow there. Take the next pixel, we know xy location, we know these 6 parameters, we can find D. So we are coming up with, in a way, some model by using only 6 parameters, we can compute optical flow at every pixel. That's called parametric model. As compared, if we have million pixels, then we will have 2 million unknowns, because every pixel have 2 unknowns. So this is called global motion model. Okay? So we want to estimate the affine transformation, and that means we want to estimate the 6 parameters of affine transformation. what we can do, we can always, whatever we have done in this course, given images, we can compute derivatives. And that's what we are going to do. We say, well, we learned this equation. This equation has to satisfy every pixel if we have the right optical flow. So we are going to do this for all the pixels. Okay? So we want to minimize this error. If the U is correct, whatever U we get by plugging that particular pixel in those two equations, if it is correct, then this has to be 0, and it has to be 0 for all the pixels. So we want to estimate U such that the sum of square error is minimized. And that's we have done many, many times. This is exactly what we did for Lucas Canade. Okay? But that was a small neighborhood. Now we are going to do the whole image. So therefore, now what we are going to do, and we know that fx is a vector, which is a special derivative, fx, fy, and we know how to compute. And ft is a temporal derivative, which we know how to compute also. So the only thing new we are going to do, that u now is not, we are not going to compute u for every pixel, but we are going to compute the a, which are the 6 parameters. Once we know that, then we can compute u for every pixel. So replace u with x of x, a, because we have defined the u for all the image, or the pixel in the image like that. Okay, so that's reasonable. Any questions so far? Yeah? Just smile a little bit. So this is not hard, it's pretty simple, right? No? You have a doubt?
Well,
Yeah.
on the right side, that makes sense.
Yeah.
Why can't I just say that u of x is a? I mean, you're saying e of a instead of e of u, but u is x of x times a.
This is the way I've defined u of x, like that. See? This is my optical flow, right? It is the two component, u is defined like that, v is defined like that. I write down like this, I can like that, like this. So that's, that's my definition of affine flow using this. So that's what I'm defining. That's one thing. Second thing is, that's the same thing. Yes? Okay. And you know this also. Yes? And this is true for every pixel. So we want to, if the u and v are correct, then this has to be 0, right? So this is up to here is like Lucas Canade. And what is E of u is an error. Error, E of u is error. Ideally the error will be 0. So we want to minimize that error. Okay?
Yeah.
So that's E of u, we just name it like that. Now comes the thing, then instead of u, I'm going to put that upper one. Because affine, I define it. Yes? Otherwise I have to compute 2 million unknowns. So that's a problem. Okay. So now that's what I have. Very good. Okay, so I have a function. I have knowns fx, fy, ft, and I have known x. These are location of the pixels. So only thing unknown is a. There's a function. I'm going to do this for every pixel, compute fx, fy, ft, and I want to compute a. X also can compute because I know the location of the pixels, x, y. So that's very easy. And
A is 6 parameter, right?
yes, here. This is a. Yes? That's a. Okay? So this is a function which is of 6 parameters. This is a function of 6 unknowns. So you want to differentiate, whenever you want to minimize, you want to differentiate equal to 0. Okay? So how will you differentiate this? This sum square, whenever you want to differentiate, it will become 2 and that thing. Then you differentiate within that. Yes? what is the derivative of ft with respect to those 6 parameters? 0, because ft, yes? And what is the derivative of this with respect to a? You will just bring that thing, the coefficient. Magic. So this, so one thing is we mentioned that instead of a, we can put a delta a, which, you know, the same thing, just replace a with delta, because we are going to do iteratively. We talked about that last time. So this is again the same, and we differentiate, and then that what we get, that 2, this whole thing, and then derivative within that, and then ft will be multiplied with this kind of thing here, and we'll bring this ft and that thing on the right side. So delta is a is unknown, everything on the left side is known, everything on the right side is known. So remember what was x? X was a matrix, yes? How many rows?
2.
How many columns?
6.
Okay, what will be x transpose? Huh?
6 by 2.
6 by 2. How about fx?
2 by 1.
Yes. And how about this one?
1 by 2.
Okay, then how about this one? So the product will be 6 by 6 matrix. This matrix will be for every pixel, because we know the x, we know fx, fy. And what is this one? What's the dimension of this?
1 by 6.
6 by 1.
6 by 1.
6 by 6 matrix multiplied by 6 by 1 matrix. Yes? This is unknown, this is the matrix 6 by 6. Many matrices added together, again 6 by 6. Each pixel give you 6 by 6 million pixels. 8 million 6 by 6 matrices, you get again 6 by 6. How about this one? What is this? 2 by 6. This one? This one? Just 1 by 1. So this will give you, what's the dimension of this? Huh? 6 by 1. Okay, so 6 by 1, 6 by 1, 6 by 6. It's a linear system. So you know how to solve linear system. You know. Yeah? Yeah, you can find inverse and, you know, Gaussian elimination, Beckford substitution, all these things. So that's it. So that is A, the uppercase A is this 6 by 6 matrix. This we will just, you know, we will interchange. Sometimes we'll call A, sometimes delta A, but that you understand these are parameters. We'll call this as a vector B. So then that's very easy that we can solve this, find these 6 parameters using this linear system. So basic components, now how we want to implement, because see, we are done with the theory. It's pretty nice, it makes sense. But we want to write a program to, you know, make it work so that it does some meaningful thing. So what are the basic components of this? So one is that we are going to do using pyramids, because it's impossible to compute the motion using one level if the motion is large. We have talked about that. Because optical flow we are going to do here also pyramid. Second thing is that, you know, after pyramid construction we are going to do motion estimation, compute these A or delta A. And then since we are using pyramids, we are going to do coarse-to-fine estimation. And so let's say we have 2 images, image H and image I. We build a pyramid like this. So it's very nice. You know, every level we reduce X by 2, Y by 2, and we get like that. And it looks like a pyramid. So if the motion is 10 at the lowest level, the next level will be 5, next will be 2.5, next will be 1.25. We are reducing. Okay? So what we are going to do, we'll compute the global flow or global motion at the highest level because their motion will be large, as we did in optical flow, very similar to that. And then we will warp that flow or that motion, and then we will compute that, use that the initial estimate, compute at this level, then keep going different levels. So that's the process of using pyramid and using this in iterative fashion, so that at the end we will refine this thing. So a little bit more detail. So we are given two images. We call the first image at t minus 1, second image at t on the right side. We build a pyramid as shown here, and we have only 3 levels, but we can have many levels if you want. So once we have the pyramid, these levels, we start with the highest level here, and we will start with some initial estimate. If you don't know initial estimate, you just assume it's 0, all zeros. But if you know some idea, we'll start with that. We will apply that motion to this image, and then we will get the image after applying that motion, or we will call a warped image. So this is a warping. We'll talk about what do we mean by warping. But basically, we will transform this image using this affine transformation. Will look a little different image. If there's only translation, we'll translate it. If there's rotation, we'll rotate it. So this will be a warped version of this image based on the initial estimate. Now we have this from the first image, this from the second image. We will solve this linear system, find that delta A. Okay? So we will, delta A0, we'll take that, and similarly we'll compute delta A1, A2, and so on. So given that delta A0, then we will add that to whatever we have before A0, that will become A1. Then we'll use that A1, go to the second level, and we can do several iterations, but let's say we just one iteration. We'll take that motion and go to this level and warp this image using this affine transformation. We get a warped image, but then motion is compensated here. And using this and using the second image, we'll again do the linear system, estimate the delta, and get that delta, add that to A1, we get A2. And we take this A2, go to the next level, warp this image with that, get the warped image, which means it's compensated, and use that, and again apply the linear system to compute delta A2. And we'll add that delta A2 to A2, and it'll become A3. So that's the idea in the using pyramid in hierarchical fashion, and estimating initially, then applying that to compensate, then looking at the residual motion, and then keep propagating in different levels. It's very similar to as we talk about Lucas Gnade with pyramid, But there we were estimating optical fluid, every pixel. Now here we are just estimating, means we are estimating these A's or delta A's. Okay? Any question so far?
So we have to, it means that we at least need to 6 level of pyramid, right?
No, I mean depending on how many, how big is the image, how big is the motion, you can just use 2 or 3 or 5 and 10. Because see, the reason we are using pyramid, as I showed you here, is that the motion we are looking at, we need to deal with the large motion. So in this case, maybe say largest motion was 10 pixel. Then we should build these many levels so that maximum at the highest level is 1 to 2 pixel. So this will be fine. But if the motion was only 5 pixel, maybe you don't need all these 4 levels. So the levels of pyramid depend on how large is motion.
But in the diagram, in every level, pyramid level, we calculate the one parameters. So I mean, maybe we need to calculate, estimate the 6 parameters. So it means we need to at least a 6 level of pyramid.
I don't understand what that has to do with. See, we are estimating 6 parameters. That number of parameters doesn't depend on the levels. You can estimate parameters, 6 parameters at one level. This is the linear system, is that right? What that has to do with the, so this is a linear system. At one level, I get fx, fi, ft every pixel, and I put in there, I can estimate the A. The reason we are doing the different levels to reduce the motion so that we can get a better estimate. Get it? Yeah, go ahead.
How do you get the, it's not clear to me, how do you calculate the delta A or out of the equation?
Yeah, this one, as I said, either we call this A or delta A. This is the same thing. So it's just instead of this equation, you can put A delta AB. The same, we are going to use exactly the same equation. I can actually change it if you want here. Which one is delta? This one? So in these equations, we are calculating, oh, this makes it small. Okay, that's fine. So, why is doing that?
I'll let you go in one direction.
Okay, you like this one? This side is good? Okay, that's good. Okay, so see now these equation, we are computing delta A in all these. We have a function which is error is a function of delta A. We differentiate with respect to delta A, we equate to 0, we find delta A. We could do this exactly the same for A.
So the function is
So that's a function. So we are saying that the change, because see remember how do we get this function? Let's look at this function here. So we say this is affine like that. So we say, this is what affine is. Then this is the same thing, yes? And when we introduce optical flow constraint equation, we did like that. So now, then we put in the define that U is in terms of X and A. So A is a motion parameters, okay? So motion parameters is, some A. Then there's a other small change in motion parameter, which will be again affine. So this equation is also true for delta A. Instead of A, I replace delta A. So then whole thing is true for delta A. Then I go here, so I have delta A, I differentiate with delta A equal to 0, and that's it. Okay?
the function is the function of the flow of how much the pixel moved actually between the
Yeah, I mean, see the notion, you have to understand what's the notion of delta A. So we have, one is A we start with, and then we want to say, there is some motion left, residual motion, which we are calling delta A. So, this whole thing, we are going to do that. So that's what we talk about here, that we are going to estimate, we start with some initial estimate, and then we take this, we warp this one, we get this. Then we use that linear system to estimate delta A. In this case, we'll call this delta A0. We add that to A0, get A1. Then we use that to warp it to get this one. Then find the delta A1, and then add that to this one, A2. Then compute, warp it, and compute delta A2, and add that to get A3. Okay?
I just have one more question to clarify. In the one slide where you differentiate, basically that arrow meant
Yeah.
that you're differentiating
Yeah.
to that function, to that function, the next function.
Yeah. The previous one?
Yeah, right.
Yeah.
So the error is just means now you're differentiating
Yeah.
to get from that
Yeah.
to that.
Because see, the error is function of delta A now. So in this thing, delta A is unknown. So we differentiate this with respect to delta A equal to 0, and we get like that. So I already told you how to get that. Okay. So yeah, Seth, please. Yeah.
How can we decide about the level of pyramids that
Yeah. Yeah, so that's, I think, related to what the question he asked. So see, the idea is that you have to ask yourself, why are we using pyramid? So that's a fundamental question. As I said, you can do without pyramid because it's a linear system, you just solve it, compute it. But it's not going to work because the motion is large. We talked about in Lucas Canade, if the motion is large, then we have to do pyramid. So that's the reason. When the motion is large, then we need to do pyramid. And the question is that how many levels of pyramid you need. So depending on, as I showed you here, that in this one, say, motion is up to 10 pixel, for example. Then we build these 4 levels. At the highest level, motion will reduce to 1.25 pixel, between 1 and 2 pixel. Okay? So therefore, in your images, if the motion is roughly 10 pixel, then you should at least use these 4 levels. Then you will be okay because the mask which we have used for FXFI, they have 2x2 mask. So that will capture. Now if the motion is 20 pixel, then you should use more levels. If motion is 5 pixel, maybe use half the levels. It depends on that.
But how are we supposed to estimate the basic motion, because we're going to estimate the global motion of the images, and we should we should guess the basic motion that it's...
Yeah, I mean, so you are saying not a basic, you are saying, well, how do you know it's 10 pixel?
Exactly.
Yeah, you will assume it will be given to you. You will know, somebody will tell you, yes? Because, just believe me, somebody will tell you. But the same thing like a threshold, you apply a threshold. Because see, we want to estimate motion, but we don't know what's a large motion. So, it's a chicken egg problem. So we'll assume that somebody told me that, well, it's at maximum 10 pixels, let's do it.
But in real application, how?
Yeah, so then see what you will do, that first is that this will depend also on the size of image, So if the size of image, is small, like say, 32 by 32, then you cannot have many levels. So at the end it will go one by one. So that's one thing. Second is that you will have some range. Say, well, okay, because you have a video, so it's a frame to frame, so 30 frames per second. So in 30th of a second, there will be some estimate you can do. So it's upon that. But if there's UAV flying, very quickly, then motion is large. If the frame rate is low, like we have some videos, frame rate is 2 frames per second, then the motion large. So all these things, but that's not important. Okay, go. That's it. Okay, let's go. So now what we have, we want to estimate the motion, global motion. We have image at t minus 1, like this, clear sequence. So we will compute the A and B. This is our linear system, and this is the system. As we talk about, everything can be computed because these are fx, fy, ft. These are location of images, pixels, and this is what we want to compute. And so we will take that A, we will warp this. It will become like that. What we want to do, we want to estimate the motion between these two such that if you apply that motion to this one, these two images look exactly same. That's the idea, that we found a motion that look the same. So now if you look at this one, they are not the same because there's a shift. See the chair there, that line, the last line is kind of close to the chair, but it's here, so it's not exactly same. So which means we need to estimate the motion to keep refining that motion so that they align. That's the idea we want to do. So the way we are going to start will be initial estimate, and which is A. These are 6 parameters, and then we will warp this image by A, and it will look like that, and still it's not aligned. And then we will so this is after warping, we have this. Then we are going to estimate the delta A, as we talked about, and we get delta A, we'll update A, so by adding, and then now warp it. Now as you saw, it moved, no? So it moved a little bit. So now that line is coming closer to the line of the chair. So keep going, it is keep refining. So we keep estimating the delta A, we keep adding, and like that, and at the end, now it's very, very close to what we wanted. Yeah.
Is that all happening in one level?
Yeah, so I have shown you just, regardless of levels, but as we talked about, that the way it's going to happen will be like this. So we will do this at one level, and we can do there many iterations.
At one level?
Yeah, then we come down, then we do iteration like that. Or just do one iteration, then come down, next iteration, so on. So it's, this is a general idea, so you can, do that, yeah.
Do we use it? Oh yeah, we do use the information because we're
Yeah.
adding the delta.
That's right, yeah.
to-
Because see that, so you are adding the residual motion, add up, so that's, because then that's what you are propagating, okay? So that's the idea here. Okay, so at the end you will get this thing working. So now it's very close. Okay, so let me show you a little demo to convince you that this actually, you can write a program to do that. And this program, actually, the student who took a class wrote this many, many years ago. Okay, so this is the very simple program, and we open, we will take the image at t-1. Let's take this one, and then we will take another image, second image at t. Let's take the scale version, which is this, and in this thing we can show the pyramids. So these are the pyramid levels, the 5 levels, and then we can run this, and here 4, let's say run by 4, so that can be a parameter of your program, so 4 levels. So that's the way it's going to run. As you see, iteratively it's refining. At the end, the output image should look like this, and actually this is looks very exactly like that. So because we started with the scale version, as you saw, and we started initial estimate all zeros, all as a. So we keep doing that. So that's the program. So let's take another example. We take open again this one, and then let's take the rotated version of that. So as you see that they're really different, and you can again see the pyramid levels. There's a lot of rotation, and says 4 levels. See, so it's changing and it becomes like that. So that is the program, and I think there's one more with just a shift open. This one?
Which programming language is
Can you guess? See how it changed. Okay, it's very nice. I think it's a C, right? I don't have access to the thing, but it's C. So this was done, long time ago, 2002. So that's that. And I think he sent a report about this. So these are the images. These are shifted. This is the this is a scale version. As you see, this big scale. This is one image. This is another image. Now we estimated the affine so that we can change this one to this one. Now this and this looks the same. Okay, this is the rotated version. As you see, there's a significant rotation between these two, so we can estimate that. And this is your clear, and we can estimate that. See that here there's a lot of space, here is not, so we are able to get exactly like that. Okay, so this is, I think, fun stuff, and it works. So let me talk a little bit about how do you do warping. So warping is very general concept which you can use lots of areas like graphics and image processing and so on. So general definition of warping is that you have an image F, you want to convert to the image H, and there's always a transformation, and that transformation is G. So what we want to do, that we want to copy each pixel x, y in F to a new location, G of x, G of y, which are defined by the transformation in the new image H. That's what warping is. So that's what this says, that the new image H will have a same gray level at G of x and G of y as xy, or this G of x is x prime and G of y is y prime. And so the transformation in case of affine transformation, we have like this. This is the displacement model, that you take x, maps to x prime using affine 2x2A matrix and translation. Or when you have the optical flow, then optical flow is affine, and we can go from this, the instantaneous model to actually also displacement model like that. We just have to subtract x prime there. So that's about transformation. So now let's look at how we can do that. So we have image here, and let's call this f of xt, and we have another image which is f x prime t minus 1, as you saw these two images. So we want to warp this image x prime t minus 1 so that it looks like the image at t. If our transformation is correct, it should look like that. And as I showed you examples, it does. So what we are going to do, that we'll call this warped image x double prime t minus 1. And it should look like this. So now we know that x prime can be obtained by subtracting u, the motion, from x, and we are assuming the motion is affine, so that's given by x plus b. So this relates to x and x prime like that. So we can, manipulate these, and we say, well, we can take x common here, so this become identity here, then a and minus b, and we can call this another matrix, identity minus a is a prime, and like that we can bring b here, and at the end we have x in terms of x prime. So if we know x prime, we can find x. Here, if we know x, we can find x prime. So, same thing. So what we can do then is, now just not to confuse this x with the warp version, so we are going to call this new one x double prime, just to make things easy like that. So x prime is equal to a bar minus inverse, and this is the same thing. So here the idea is we'll convert this to this one. This is x prime, we'll call this x double prime. So now simple way will be that you go through each pixel here. You know its coordinate, x prime. Plug in here. You know the transformation. You know the b, you know the a. All this you find x double prime. And copy the gray level of that pixel here. Again, go to the next pixel, again find where it maps to, go here, and copy the gray level of that pixel here. You do this for all the pixels. That's called warping. Okay? It's a pretty simple idea. So warping, you need to know what's the transformation. And transformation we have estimated, which is affine. So then so that's good. So this, what you ultimately will have is, this is the video. Now see, we can do this for every frame, every pair. 1 to 2, 1 to 3, 1 to 4, 1 to 5. Now this is your thing. So let's turn off the lights, and for a moment. Which light should I turn off? Front? Okay, you like it now? So there's a video. Is there are cars moving and the camera moving? Where is this from? Anybody can guess? Huh? Airplane. Of course it's from airplane. but where, this is in US. Where is it? Tennessee. Where else? Colorado? Orlando. Anybody else? Any other? Who like football? This is one of the famous football places. Football. No, real football. American football. So where is it? This is Ohio State campus. Okay, so you saw that it's moving, airplanes moving, everything is moving here, and that's a problem. Now if you do this, what I just explained to you, now see that streets are not moving, It's amazing, is that right? But the cars are still moving, So little cars, they are still moving. So that's the beauty of science.
Google can do that for your...
Huh?
I think YouTube can do that for your video.
Yeah. But this is a theory. So I'm telling you how you can make a YouTube kind of company, using this. Did you guys know the guy who did come up with HOG, the histogram gradient orientation? His company was bought by Google 400 million. 400 million, It's 7 people company. So you are looking billions, after you finish this class, you can. But it is hard, so you have to spend hours, sit down, do the math. Without math, it's not going to happen. Okay, so let's play these together. What happens when play? So see, so it's saying how it's warping. These images are changing, and all this thing, but it's keeping the global motion constant. So that's that, and let's look at other example here. So this is a real football, and this is, where this is? It's written here, is it right? Which football team is it? Oregon or something? Yeah. So then this is the compensated motion. Okay, and then you can compute optical flow, which is shown here. where the direction of motion is shown by this wheel. The guy moving this way is red, the guy moving this way is blue, and so on. So that's the fun stuff. Okay, so now you can take this and make a mosaic, and it'll be like this. You can stitch these frames together, then what happened here? Let's see. So, okay. Maybe it's thinking. Anyway, so this, I don't have this video or something. Yeah, there's another thing, and you can make a mosaic like this. So let's just skip that. Okay, so now this was a fine transformation, and this is the first transformation, and it uses approximations. Now we are going to look at the next one, which is much more sophisticated, and this method will do projective transformation, the homography. So these are the authors. One is Main Picard and other is Picard. This is a professor, and he was a student, MIT professor. They came up with this method. Actually, she will be here next month, November, give a talk in Orlando on the conference. So the idea is that the affine model will not capture the pan and tilt, as we have been talking about that rotation matrix, the 2x2 matrix. It is only rotation on z-axis. Okay, it does not have rotation on x and y-axis. That's called pan and tilt. And also, it will not capture what is called keystoning, the perspective effect. This is the example of keystoning. As you see that you can take pictures, it can look like that, and it's a real camera picture. That's what the perspective transformation does. And there are actually methods, like from Adobe you can correct that and you get from this way. But the real world picture is like this. The other thing, what is called chirping, and this is the chirping effect, and which is under perspective projection. There's increasing or decreasing a spatial frequency. As you saw in these windows, the frequency is changing per area, and that effect you cannot capture in the affine transformation. So for that, you need more sophisticated model called projective transformation or the homography, and that's what we are going to do. And also, these are the examples. I think very similar example I gave you last time. So if the original image is like this, then affine can get you like this. Bilinear transformation can get you like this. So these are non-chirping models that frequency cannot increase, decrease. You cannot model that impact. But this is the projective transformation. This has the chirping. These are all chirping models. And this is a pseudo-perspective. As we talk about, this is a biquadratic and so on. And these are the equations, as you remember, we went through that. So we want to talk about how we can estimate projective flow, again using the same framework. See, that's what I always try to do, that once you understand one thing, then we want to keep building on it. So we'll talk about how to estimate projective, very similar to what we talk about affine, so which is very nice. So what we're going to say, again, we are going to use this optical flow concern equation like this, and that's like that in the vector form. And this is our projective transformation. X prime is given by Ax plus B, C transpose X plus 1. If the C is 0, then this is the affine. So affine is special case of projective. Okay? So now for the optical flow, we can write down X prime minus X is optical flow. So if you subtract from here X, so this is we are going from displacement model. Displacement model means x and x prime. The instantaneous model means there's an optical flow, u, the velocity. So this is the instantaneous model. So now, we'll use the same thing. We have an error. We want to estimate u. U in this case is much more complicated as compared to what you had before, and actually more unknowns, as you saw here, that we have 4 unknowns here, 2 unknowns here, and 2 unknowns here. There are 8 unknowns as compared to 6 unknowns before. Okay, so, but we are going to follow the same thing, and instead of u, we are going to put the projective transformation. So this is the projective transformation minus x. As you see here, this is u. U is defined like that. So we just put it there. In affine, u was only this. Now here, we put it like that. Okay? So rest is very similar, exactly same. So now, what is the easiest thing we can do? Because see, the reason is hard because there's a denominator. Whenever the denominator has become nonlinear, is a problem. In the upstairs, when you're x plus b, there's no denominator. The numerator is easy. We can do that. So we need to get rid of the denominator. And what can we do? To get rid of denominator, you take the denominator, multiply every element, then we'll get rid of it. Is that right? And since the error ideally is 0, so if you multiply anything with 0, it will be 0. It won't have impact. So that's what's going to happen. So we'll multiply Cx transpose plus 1 everything here. So it will become like that. Ax plus b, since it already had denominator, it won't have impact. They will cancel. Then we have the fx multiplied by Cx transpose plus 1, so which is this term multiplied by this, which is here, and then the ft multiplied by this. So now here we have all numerator terms, and we can follow exactly same thing as we did for affine. We have error, we have unknowns. Now here unknowns are 8. The A's, 4 A's, 4 B's, 4 C, 2 C's. 4 A's, 2 B's, 2 C's. And you can do this in the homework. See, you want to make 400 million, is that right? I mean, that's not easy. So you will end up like that. So again, you will end up with a linear system. Remember linear system? A, small a is equal to B. It's exactly same. It's a linear system. So that is a matrix vector which we want to compute. This A now is 8 unknowns, and this is again a vector. So, and A is A1, A2, B1, A3, A4, B2, C1, C2, and 5 is this. fxx, fxy, fx, fyx, fy, and just keep going. And then just use the same program. So the challenge is that you go from here to here, to this one, no? And you can do that. If you stay up night, I can guarantee you can work it out, and you will feel very good. Okay, that's the breakthrough. That's what we are. That's a challenge. Instead of watching TV and wasting your time, this is fun. Okay, so this is projective flow, and the only thing is that it's a weighted, because we multiply with that denominator thing. So that's what we are getting. So now let's say we want to do the unweighted, the real one. And what we are going to do, that we will take, remember we were talking about the approximation of projective transformation. And one approximation is pseudo-perspective. And the way we did it, that we are going to do the Taylor series of this, and by removing 2 square terms and considering 4 remaining terms, and this is a pseudo-perspective transformation, which is approximation of the pseudo-perspective, the projective. So whenever you have a non-linearity, you always use a Taylor series to linearize it. And that's what we have done here. So now this is very similar to affine. So again, there's no denominator. So you can use that. You can do another one, which is bilinear. Again, we have talked about this. Taylor series removing square terms. This is a bilinear. So we can just plug in that in also. So if you do that, then you will have, again, same thing. You have the optical flow constraint equation. In one case, it will be pseudo-perspective, and we'll minimize. And if you do pseudo-perspective, we will get these terms, which is fx multiplied by xy, fx, fxy, and all this thing. And this for bilinear, and this will be for pseudo-perspective. So the form is similar, and again, this end up with a linear system. This matrix is now big, 8 by 8 instead of 6 by 6, 8 unknowns, but the same idea. So what that means, that we are able to do now the approximation of projective, pseudo-perspective, or bilinear, very similar to what we did affine. And of course we can do weighted affine, which just multiply that. So now what this man Picard did, that they started with the approximate model like a pseudo-perspective. So once you estimate that, then you can refine that model to get the true projective model. And that was, very interesting, and actually they got very good results. So we are going to estimate Q using approximate model, for example, bilinear model, or you can use pseudo-perspective. Then, so Q is the parameters of those 8 parameters. Then we have 2 images, and we have estimated this, say, pseudo-perspective model. Now we can select 4 points in this image. Using the pseudo-perspective approximation, we can find corresponding point in the second image. Now we have correspondence of these points here, points here. Then we can estimate the full projective model, as we talked about last time. So that's what they did, and that actually make a difference. So here is estimate the approximate model, then take the 4 points, and from Q we estimate the P, which is the real projective. So here is the example. Let's say we are taking points. Here take many points. So here is corners, but you actually need to take only 4. 1 here, maybe 4. And using this, since we already know that how each of these points maps to here, because we have estimated the pseudo-perspective, and there we have the equations here. Okay? We have these equations here. We know that given our, the x, we can find out x prime. So we can find those pixels in the second image. So once we know that, those points, then normally if you don't know, then you have to do SIFT, and you can match, and then you can estimate homography. And this is what I talked to you before, that if we know the correspondences, 4 points, using the correspondences, using the pseudo-perspective, which is approximate, then go to projective, this is the model, and now it's easy, because you can write down like this, and here again 8 parameters, but we know the correspondences, and we can do the least square fit as we have done before. So keep in mind what we have talked about so far. There we are not assuming we know the correspondence. We have just 2 images. We compute fx, fy, ft, and all that. We can compute optical flow. Using all that we can take affine, all that we can compute pseudo-perspective, bilinear and so on. Spatio-temporal derivative, which is called direct method. So that's what we discussed. Now, if you take these two images like I'm showing here, another way to find the transformation between two images is you apply, say, Harris corner on this, Harris corner on this, and then compute shift descriptor on each, and then you find the match. Well, this point matches with which? To match with all that is the best match. This point matches with this. So now you have correspondences. So you have x, y, you have x prime, y prime. Given the correspondence, then you can estimate the projective transformation. It's easy. So there are two different ways to do it. One is called direct method, which uses the spatio-temporal derivatives. Other uses the points, the descriptor matching. Then it's very simple. So simple least square fit, which I explained that before. So that's, I think, so final algorithm, we'll have again the Gaussian, and then we'll estimate the approximate model, and then we will relate that. So I'm going to skip that. So at the end of this, let's see here. So this is the guy. So actually, he was the first person to start this wearable computers, Steve Mann. And so he went through different versions of these. He used to wear these things and walk around MIT campus. And when he's walking around the camera, you see very small view. So he said, well, I can take a little video and stitch them together, I can see a bigger view. And that's the idea of what he did. And he's a professor now at University of Toronto. And this is a mosaic. And if you do only Affine has a problem. Mosaic for that. Building, you went to Walmart, so you can look at the cashier and you want to see the whole thing. So you can do this kind of thing here. And the Scientific American mosaic. And he went to have a lunch in a Chinese restaurant with two Chinese girls. He was sitting there, then he can see this thing. Okay? So he was in MIT Media Lab. So as we talked about that, this is application in the UAV video. So we have this COCO system, which uses these parts of alignment. And the most important part is the compensation, motion compensation. And you will have to do that, and we are doing here that each of these estimated the motion, and we are building the mosaic increment like this. This is another one. I think I have already showed you this one. Yeah, so like that. Okay. So we will stop it here.